one or two more examples of direction one when we start from we're evaluating integrals. So if you remember the steps of the program we're following, so one of the steps is choosing this additional path, and then proving that the integral over this path becomes small when r goes to infinity. So here is another example when this is possible. So one example was this ratio of two polynomials with denominator having a degree at least +2 to numerator. Another example is like this. So theorem. Suppose we have f a meromorphic function, so only poles on complex numbers, and no poles in real numbers. So in a way it's important because next example after this will show what to do when poles are on real axes. So suppose that indeed, so we plan to complete the interval by half circle again. So suppose the limit for r going to infinity f of r is small, and suppose that we choose lambda greater than 0. So it's important that it's greater than 0. Maybe I will not use it in the calculation because I don't plan to follow the calculation in detail, but the choice of positive number is important. Then the integral from minus infinity to infinity f of x times e to I lambda x. So as we understand it, it's not one integral, it's two integrals, the real part and the imaginary part. But dx equals 2 pi I sum of residues, so singularities in upper half plane. Residues f1z exponent I lambda z at aj. Yeah. So remark, in practice, one evaluates the real part of this integral or imaginary part of this integral. Of course, then you apply real part and imaginary part to the right hand side. So, so I'll give hint of the proof. And then example how it works. So as before, even our conditions are about half circle. So as before, choose gamma add to be this. So what you really need to estimate is integral, well, I'll just substitute from 0 to phi r exponent of it, so this is the value of the function, times e I lambda I r t dt. So then this is less or equal then this maximum on this times the integral of, and now we see that sign of lambda was important because I times I gives us -1. Again from 0 to 5. And then the point is that you can make this small. So you can estimate this as small. So this maximum is bounded, and this can be made small. So in total, this tends to 0. Yeah. So outcome. This 2 pi I sum of residues is limit r going to infinity integral of gamma r f of z e to I lambda z dz plus integral over gamma ad f of z I lambda z. Now the second summand has limit 0. So then we get simply what we want to do. So, so example of application of this theorem is when you so the book says the integral minus infinity to infinity, so it will be the real one, x sine of lambda x, and lambda is positive, over x squared plus 1 dx. And now we realize that we are in the situation as before, because we can write f of x is x over x squared plus 1. And notice that the estimate for f itself wouldn't work, because the difference of powers is not 2 but 1. So this second factor is important, but sine of lambda x is imaginary part of e to I lambda x, x real. So our function in total will be so our function will be, so we'll look for residues, look for singularities. Of x I around x. Oh, sorry, z. Z squared plus 1. I won't even continue because singularities, of course, come from denominator, so it comes from I and minus I. You can calculate residues and you can see what's going on. But the point is that you have some integral which looks very much real valued integral, but in fact it fits very well into this scheme. Now another almost example, so I won't go very far in the proof, but at least I want to mention this example. So this is what to do with poles in real axis. So the example is like this. So we want to evaluate integral from minus infinity to infinity sine of x over x dx. Now notice that as a function, as a real function, we know that the limit to 0 exists, right? So it's a continuous function. So yeah, remark sine of x over x is a nice continuous function on the whole real line. However, sine of x over x, of course, is the imaginary part of e to I z over z on real line. So now this function has a pole at 0. So I mean it's obvious because the e I z over z has a singularity at 0. So what to do? So the point is that we make double limit, make a closed curve, call it gamma, well, I don't know. I need 2 parameters, so I'll draw it. So of course we'll be taking limit over intervals from minus r to r, and somewhere here there's a point 0, which is problematic. So it will contribute to residues. So the way out is to choose a very small radius r here and go around it like this. So our integration, our complex integration will be like this, and then you need to complete it as before. Only we have freedom in the choice of this additional curve, and in this particular case, the book suggests, which actually shows that there's something to think about when you're looking at exercises to solve, which curve helps you more. So this is, I mean, these are the vertical lines, and this is the horizontal line at IR. So then our limit. So our integral from minus infinity to infinity sine of z over z, sorry, sine of x over x dx will be, well, imaginary part of sum of this, so call this gamma 0 because it's around 0, and this gamma n as before, so this whole thing. So it will be the imaginary part of integral from minus r to minus r e to I z over z dz. So limit. Limit. And the limit is double limit for capital R going to infinity and small r going to 0, plus integral over gamma 0 plus integral from r to r e I z z dz. Sorry, I wrote something wrong. I wanted to say this, that these two summands, when r going to infinity and small r going to 0, give us this whole integral. Yeah, and to apply Cauchy residue theorem, we need to compute the whole integral. Cauchy residue theorem for gamma, which is, so to say, gamma minus r, union gamma 0, union gamma r, union gamma n. And then, yeah, estimate and calculate. Estimate gamma n. Calculate to find the so if you yes, I won't do this in detail. Again, I want to pass to sums of series. But one remark is, if you ignored this gamma 0, this part, this, your answer would be wrong. By a factor 2. So, I mean, the only singular point is 0, so the residue will be given by integration over this whole circle of something. Now, when you add this additional part, you subtract half of the circle. So your residue will contribute differently when you, I mean, half of it will cancel out with this part. So if you do it stupidly, the answer will be twice the real answer.
What is wrong with choosing the upper small circle instead of the other one?
So, I mean, you'll simply get 0.
Yeah, and why it's not valid? Because it is still a closed curve, right?
I mean, your estimate for this integral will be 0. You get 0 equals to 0. So, yeah. I mean, if you do it like this, then your actual answer for integration will turn out to be 0. Yeah, so now let me pass to summation of series. So evaluating some series. So evaluating. So I'll give you first main idea which shows where series come from. Series are sums over integers, or maybe positive integers. So the main idea is that the function 1 over sine of say pi z has poles, has simple poles at all z equal to n, which is an integer number. So you can take some other function. So take f of z, holomorphic, for example, or maybe even meromorphic. Well, let's say holomorphic on complex numbers. Then f of z over sine z also has simple poles at z integers. And then you make direct calculation of residues. So direct calculation of residues. So I won't do it on the blackboard, I'll just state it. So there are two examples. So for f of z over sine phi z at the point n, the residue is f is holomorphic, it's a simple pole, then we know that the residue basically is expressible via the value of the function, and indeed it's f of n over pi, and then minus 1 to the n. So, and if we do the same also with cosine in the numerator, the sign will here will disappear. So the residue of f of z times cosine of pi z over sine at n is just f of n over pi. So this means that so this is still not an example, but idea how to do it. So that, this means that suppose we want to evaluate. I mean, these are all singular points of these functions. We want to evaluate sum from k equals minus n and then to m f of k and then or sum k equals minus n to m just f of k. then we see that we're doing residues, and this means that this thing is 1 over 2I, because pi is in the formula, integral over gamma n m, f of z over sine of phi z dz, and this is 1 over 2I integral of gamma n m. I'll explain what gamma n m is. F of z cosine of z of pi z over sine of pi z dz. Now I'll draw gamma n m. It's any closed path which, so we have these integer points, minus n plus 1 m. Now we take any closed path going around all of them. This is gamma n m. And the choice of the path is ours. And then, I mean, what I wrote is application of Cauchy residue theorem, because left-hand side is a residue formula, so sum over residues at these points for this particular function, and right-hand side is the integral. So then, if right-hand side is evaluated nicely by some other method, then you can pass to the limit and get the sums. Right, so I'll write this down as a principle, and then we'll do one example. Evaluate right-hand side independently, which means that you use some other method but the residue formula. Maybe it's a nice integral which can be simply taken. Then pass the limit n goes to infinity and m goes to infinity, and then you get sum from minus infinity to infinity of minus 1 to the k, f of k, or sum of k equals minus infinity to infinity, f of k. Also, sometimes the function is even, which means that the value at k and minus k is the same. Then actually you'll be twice taking the sum from 0, from 1 to infinity. So now the basic example. So I remember that there are such exercises in the book, in the final assignment. So now let's do example. So certainly it's the one from the book. Let's do so we want to evaluate let's say 1 minus 1 over 2 squared plus 1 over 3 squared minus so on. So this is sum k equal 1 to infinity minus 1 to k minus 1 1 over k squared. Okay, so this is what we want to take the sum of. So we notice, so the function, so function suspect is f of z which is 1 over z squared. And now we see that there is a problem at 0. So see the problem at 0. Yeah. So then we take the function so I'll choose a path, but right now take the function 1 over z squared. Since it's alternating sum, we should use, there are two formulas with signs and without signs. So with signs, it's 1 over sine over pi z, right? So 1 over the square sine over pi z. So now the curve. Maybe I'll continue here. So the curve, it will be called fmn, and it's like this. So there's real axis. So this is minus, say, m minus 1/2. This is n plus 1/2. So in particular points, minus m up to n are here. So this is our curve of integration. I don't even want to do the estimates, but it happens that, so you calculate that limit n infinity m infinity integral over f m n of 1 over z squared sine of pi z dz is simply 0. Then this means the following. So right hand side will be simply 0. But left hand side is still different from what we want to evaluate. So let me write this down. The right hand side is 0, but left hand side is, so the function is even, so it's twice sum from k equals 1 to infinity minus 1 to the k 1 over k squared plus residue of this function. At 0. So these are contributions from integers, both positive and negative, which are not 0, and then there's a contribution from 0. So it turns out that what we really need to find, so sum k equals 1 to infinity minus 1 to k minus 1, notice the difference in signs, 1 over k squared, is 1/2 of residue only I think I lost 5. Yeah, so this should be 2 pi I here, sorry, because it's integration. Yeah. This function. At 0. Now the remaining part is calculating this residue, and it's a job by itself. So how to find the residue? Residue at 0. So the idea is to find series at 0. Find Laurent series. Of the function. At 0. Let's give it a try. So first of all, series for sine of, let's say, sine of z. So I need only the beginning. So sine of z starts from z minus z cubed over 3 factorial, so 6, plus so on. So the next powers is z to the 5 over 5 factorial, but the point is that this power is high. Now then sine of z over z has series 1 minus z squared over 6 plus, and so on, plus z to the 4th over 5 factorial minus so on. So now we want one series for inverse function. At 0. And I'll explain how to do it. So you do it, so you use linear equations to find coefficients. So in principle you can find all coefficients. So let's write what we want. So z over sine z. So this series starts from 1, so inverse series also should start from 1. So this will be 1 plus k1z plus k2z squared plus so on. Which means that if we take this series and multiply it by series we know, plus 0z minus 1 over 6 z squared plus so on, it should be 1 plus 0z plus 0z squared, so on. So if you compare, you'll get that k1 plus 0 equals 0. So this is coefficient by z. Then k2 minus 1, 6 plus k1 times 0 equals 0. So then k2 actually equals 6, 1 over 6. And that's what we wanted. So, this is basically one of the last things I'll write on the blackboard. So I think this calculation with series is important independently. So sometimes you can find first coefficients of inverse series by solving such linear equations. So yeah, so we get that 1 over z squared sine of phi z equals 1 over pi z cubed 1 plus pi squared z squared over 6, and then so on. So this is my coefficient 1 over 6, pi squared appear because there's pi z here. So then we see that coefficient by 1 over z is exactly pi over 6. So a residue of 1 over z squared sine of pi z at 0 is pi over 6. Now, when we substitute, I did something wrong. Namely, I lost, as predictable, I lost 2i. So I get that sum we're interested in. So 2i cancel out with this 2i is 1/2 times pi over 6. So in the end, it's pi squared over 12. It's quite a complicated calculation, and as you see, it's full of tricks. One trick was to guess that you should use integrals for summation. Second trick was to choose this curve of integration and see that the actual integral is 0, and then the last trick was to carefully calculate the contribution of 0. So contribution was 0, what of 0 was actually what gives you the answer. So in a way it's a strange situation because you use integral formula, but the actual answer is given by one point, by the point 0. Good. Great. I wish you good luck with the final exercise. And next week you'll have meetings with your PAs who are supposed to help.